Hello everyone, myself Dr. Rajesh Prasad. I'm currently working as professor in CSE at Akgec Engineering College, Ghaziabad. So today I'm going to discuss sorting techniques like advanced analysis and methods. So I'm going to discuss two type of sorting technique. One is like divide and conquer based quick sorting and its complete analysis in all the cases, best average and worst cases partitioning, and we'll talk about its randomized version, which is very important, especially if we are talking about randomization algorithm. And another category is like sorting in linear time counting sort. We know that most of the methods like other than linear method, they are based on somehow comparing the elements, right? But we'll see that counting sort is not going to compare any number of element. It is just like going to count the frequency. After counting the frequency, it is going to place into the proper positions. Okay, so let's discuss with the quick sort. Yes. So quick sort, as its name suggests, let me just like because it is not like this is fastest sorting scheme. Is not like that. So we know that if element is already in sorted order, let's say this like that, this, okay. So quick sort is not a better choice for this kind of questions, right? If you know it is already in sorted order, so quick sort is not better than even bubble sort, because in this situation we'll say that quick sort running time is theta n square in this type of situation, while insertion and bubble sort will be giving only theta n time actually. So in this type of situation, quick sort will be better than like bubble sort is better than this. So generally quick sort is very helpful whenever data is like in mixed order, not like arranged order, right? We'll see that this type of method, this type of data is not suitable for quick sort. If data is already in the sorted order, we should go on the quick bubble sort and like other sorting techniques. We'll see that randomize and then think about counting sort. So general procedure is very simple. This applied divide and conquer approach. Here, generally we are dividing the problem, but we are not conquering, because after dividing, we'll see that partitioning element is already placed into proper position. Fundamental is very clear. In this method of quick sort, we assume that this is an array, right? A is an array where P is lower side and R is upper side. Okay. So we are assuming that, there is a partitioning element. Okay. We assume that any element can be taken as partitioning element depending on the situation. Many partitioning elements are there. Many like partitioning element. Any element can be taken. Some algorithm can take last element as partitioning. Some they are taking beginning, or some they can take any other element. So there are many procedures for partitioning the array. Suppose we are partitioning the element and Q is the position of partition element. So generally, this AQ actually is placed into proper position. So left to this AQ, all elements are less than, okay, and right to AQ, all elements are greater than. Okay, this is the actually concept. So in this situation, in this algorithm, I am assuming the last element as a partitioning element. So let's understand the question. Like this is the quick sort partition PR. We are assuming that A is an array and P is lower bound and R is an upper bound. Okay. So what we are going to do, this is the array, this is the one, P and R. Clear? So we are assuming that this is the Q, first partition. Assume that this is Q is the position of partitioning element. Clear? So after partitioning, you will return this procedure will return the position of partitioning element. I am assuming that this is Q. Then we are going to apply the quick sort on this left hand side, P Q minus 1, and right quick sort on right hand side, q plus 1 to r, q plus 1 to r. This is the right hand side, this is the left hand side, and this is right hand side. Okay, so this is the first. So main important rule is of the partition, how to partition an array. Okay, so let us assume that one question. Let's see. So suppose we have 4, 2, 1, 6, 9 and 0, 3. Okay, let's say this question as an example. So if this partitioning element is taking the last element as partitioning element. So we are assuming this is the P and this is the R. We take last element as the partitioning element. So this is the line number 1. First it is taking the last element as the partitioning element. Like here, whatever P you are choosing, I will always be less than P1. So I is P minus 1. So these are the initialization. First one, take the last element as partitioning element. Whatever P you are taking, I should be 1 smaller than that. Okay. And now run a loop from P to R minus 1. This is J, which is running from P to R minus 1. So this is the next method. What you are going to do, compare AJ and this guy, partitioning element. If 4 less than or equal to 2, 3, no, this is not the one. So continue, J will become this, I remain the same. Okay, here 2 less than or equal to 3, correct? Yes, 2 less than or equal to 3. If it is the case, so what you are going to do, actually we are trying to get the position for this partitioning element. That is the process. Okay, so in this situation, increment I. So what is question of 4, 2, 1, 6, 9, 0 and 3. I is here. And J automatically will increase. J automatic will increase. Again, if you compare 1 and 3, 1 less than or equal to 3, correct? Yes. So in this situation, I will increase. Okay. So this is 4, 2, 1, 6, 9, 0, 3 and I is pointing here and J is auto increment. You see here, J will go up to this. Okay. So I is incremented. Again, 6 less than or equal to 3. No, this is not true. Then again 9, keep incrementing, 9 less than or equal to 3, no. Now 0 less than or equal to 3, yes. So in this situation, I will increase, right? So what is now 4, 2, 1, 6, 9, 0, 3. I will increase. So I will go to this point, clear? I will go to this point. And here J will finish. J cannot go beyond this. So J finish. I has increased. Okay. So I is increased and after doing this, so after increasing I, you have to exchange AI and AJ. Like here, if we start here, so you see I was not here, then 2, yes. So 1 less than or equal to 3. Okay, look at here. 4 less than or equal to 3, no. Then I was here. Okay, so 2 less than or equal to 3, correct. So then in that situation, I is increased and AI and AJ exchange. So there was no like AI and AJ in exchange. Okay, so let's start it again. Look at here. If in this situation, let's say if we say the 4, 2, 1, 6, 9, 0, 3, 6, 9, 0, 3. Okay. So this is the position of partitioning element. This is 3. We start with I here and J start from here. 4 less than or equal to 3. No. So that means J will increase here. Now I remain here. For it is situation is like here 6, 9, 0, 3. Now J is here. Okay. And I is here. Clear? So okay. So now here 2 less than or equal to 3. Correct. 2 less than or equal to 3, correct, yes. So if this is the situation, then increase I is increased, okay, I is increased, then AI and AJ exchange, that means this guy and this guy will exchange. So 2, 4, 1, 6, 9, 0 and 3. I will be here and J will automatic increase, clear? Okay, again 1 less than or equal to 3, I increase to this point and AI and AJ exchange. So what is answer? 2, 1, 4, 6, 9, 0 and 3. Clear? So I is going to be here and J will point here. J will again point here. So again if you look at here, 6 less than or equal to 3, no, J will go here. 9 less than or equal to 3, no, J will go here. Again 0 less than or equal to 3, correct, yes. So correct, then in that situation I is increased, okay, and then AI and AJ exchange. So what is answer? 2, 1 and then 0, okay, and 6, 9 and then 4, okay, and then this is 3. J is finished, okay. After this situation and I will be here, I will be pointing to this position. You see I was here, okay. After finishing this, exchange AI plus 1 and AJ. This guy is exchanged to get the final one pass of the partition. 2, 1, 0 and then 3, 9, 4 and 6. Okay, so and return I plus 1. Remember your I was here. Okay, so return I plus 1 means this is the position of partitioning element. And now we can see that left to this is the all element less than or equal to this, and right to this all elements are greater than or equal to 3. That means this is the correct partition. And now you can apply the same method to 210 and you can apply the same method to 946 and we'll say that it will be sorted, right? So if you apply the same method to 210, you will see that this is the x is 0 and here will be I. Start a loop from here to here, okay? So this is J, clear? And now 2 less than or equal to 0, no. 2 not less than or equal to 0, increase this, J is here. Again 1 less than or equal to 0, no, finish. So after finishing, AI plus 1 and AR is exchange. So this guy is exchange. So you will be getting 0, 1, 2. So you look at here, this is the position of partitioning element. Right is greater, left is nothing. So again we can start with this. We'll see that this is the sorted order, right? Similarly, you can also go ahead and start the same method with 946. So after doing this, you will see that array is going to be sorted, right? So main important thing is how to analyze it. Okay, so first one is the worst case partitioning. Worst case partitioning means that, you know, like worst case partitioning. This is important case. Worst case partitioning means array is already sorted in sorted order, like see 1, 4, 5, 6, 7 and 8, right? So we know that if we are taking this as a partition element, let's say x, so of course all elements are less than x and there are no element right in the right hand side, okay? So if this is known as the worst case partitioning. So if you are solving this type of question, again take this partitioning element, you will see that left hand side you will see the element, right hand side you will not see the element. So if we think about recurrence relation for this question, total problem is n, Tn minus 1. Left hand side remain n minus 1, right hand side remain no element 0, and this process of partitioning is continued up to n minus 1 times, okay? So if you start simplifying this, Tn minus 1 plus this guy can be taken as Cn. Take it as a constant. And Tn is going to be this. And if we apply this solution using recursion tree method, you will see that Tn is going to be theta n square. So worst case partitioning quicksort is not better approach, right? Yeah. Second approach is like best case partitioning. This is important technique, like best case partitioning means almost partitioning element is in the half of the method, right? This is the partitioning element. Left hand side is this and right hand side is this. Is this type of recurrence relation is Tn is Tn by 2, half of almost, right? Plus this is the number of time you are calling the partition, right? Yes. So if we see this solution using a master method, so this is n log n. So best quicksort is very well working if data is already in this order, that it is partitioning in the half of order. Okay. So this is important case when we are talking about balance partitioning. This is important, right? Balance partitioning, that means if you have element of size 5, so this can be the situation that it is not exactly coming. Suppose size of the array is 5, it should be the case that this is n by 5 and this is 4n by 5. This type of situation may occur, right? So if you are just taking this Tn by 4n by 5, this is number of time you are calling the partition. If you use recursion tree method for solving this, we will see that this is the solution. Okay, Tn 4n by 5. Okay, so if we start taking the longest route, we will see that solution of this recursion tree is n log n, and which is going to be approximated as this. So this is important method when we are talking about balance partitioning. Okay, so randomized quicksort can also be possible. Right now what we have been taking, like is very simple, that this is array. Okay, this is P and this is R. Clear? And you are applying any element. Let's say instead of taking the last element as a partition element, take any element as partitioning element. And very simple, first one, before applying like partition, exchange this. This is how. Take any random number between P to R, take its index, exchange AR and AI. Now this is, and you can start partitioning now. You see, once it is exchanged over there, then you can start partitioning the array. So randomized quicksort is very simple. You apply the randomized partition and then randomized quicksort and this one in the left hand side and the right hand side. This method is better because you are not interested in choosing any element. Any element can be taken as partitioning element. Okay, so we have seen that whether it is quicksort, merge sort, bubble sort or insertion sort, actually somehow we are comparing the element. Look at here. We are comparing these elements. Somewhere there is a comparison, right? But like counting sort is not actually comparing. It is just counting the element. So this is based on the frequency count, and this is coming under the category of sorting in linear time. Linear time means it is going to be in the order of n. So sorting, counting sort, assume that elements are from in the range of 0 to k, where k is k is big O of n. Maximum element should not be more than the number of elements. This should be in the limit. Okay, k is big O of n. So let's understand this counting sort. Let's say this is stable sorting scheme. 2, 1, 0, 3 and 1, let's say 5. Okay, so here k, if you just like take k is here 5, highest element in the array. This 1 and 1 is repeated. In order to get the stability check, make sure that this is marked with any other number, so that after sorting we should always make sure that one is coming before one star. Okay, so this algorithm is making an array of count. Okay, this is the count array. Count array is basically from 0 to k. Okay, so 0, 1, 2, 3, 4 and then 5. K. 0 to k. Okay, so first one, make all this index as 0. We don't know, we are going to count, right? After this one, we know we are counting the element. So then again this is going to be updated 0, 1, 2, 3, 4 and 5. Okay, so count of 0, count of like here 1 to like this is array A, and we are assuming this its index from 1, 2, 3, 4 and 1, 2, 3, 4, 5 and 6. We are assuming its index from 1, 2, 3, 4, 5, 6, right? So we are just counting. So look at here, count of 2. Count of 2, how many places it is coming? It is 1. And this is the counting. Count of 1. Count of 1 is going to be 2. Count of again 0. Count of 0 is only 1. Count of 3 is only 1. Okay. Count of 4 is nothing. 4 is not appearing. And count of 5 is 1. So this is the counting technique, just like counting the number of occurrence. After counting, what is remaining now is cumulative count. Just calculate the cumulative frequency. Okay, so here then I start from 1 to k. So 0, 1, 2, 3, 4 and then 5. Okay, so C0 remain the same thing, 1, and next value is added with previous one, so 3, and then 3 plus 1 become 4, 4 plus 1 become 5, 5 plus 0 become 5, 5 plus 1 become 6. This denote the number of element less than or equal to this index. You see that number of element less than or equal to 0 is 1. Number of element less than or equal to 1 is 3. Yes, correct. Number of element less than or equal to 2, they are 4. Number of element less than or equal to 3, they are 5. Yes, they are 5. Yes, number of element less than or equal to 4. So this is count array final. Okay, now they take another array B. This is the output array. This C is clear. Take another array B. Start from 1, 2, 3 and then 4, then 5 and 6. Start from the last element of this guy, A6, find out A6, start from the last element A6. A6 is going to 5. Okay, consult C5, this is 6. So B6 is going to be replaced with this value 5, correct. Okay, and then counting of this value is decreased. Counting of this is decreased to 5. This is the next step. Okay, again go to this one star, C A5. A5 is 1, and now consult C1. C1 is 3. So this C1 is 3. Okay, so this is going to be in the 1 star is going to be here, and this is decreased to 2. Simple. Okay, so this is 1 star. Okay, again go to this backward. This is like C4 is 3. Consult C3. C3 is 5. So B5 is going to be this value. This is going to be this, and this is decreased by 1. Clear. Okay, go to this value C3. Now you see this is go to A3 is 0. Go to C0. C0 is going to be 1. So now B1 is going to be this value. B1 is going to be 0. this is the one, and replace it by 0. Clear? Again, look at here, go to this point. Okay, A2 is 1, consult C1 is 2, and B2 is going to be 1. This is placed over here. This is decreased by 1. Similarly, if you go to this point, A1 is 2. So consult C2. Okay, C2 is going to be 4. So B4 is going to be here, and this is replaced by this, and this is decreased by C. You will see that B array is totally sorted, right? So there is one important thing. If you change it from 1 to n, array will be still sorted, but that will not be stable. It may change these directions, right? So yes, so you see, this is the references. Thank you for watching.